If you have not done so already in our previous video, please go and play around with your Desmos derivative machine. If you are watching this during class, then let's read through this and see what you should be doing. Derivatives of polynomial functions. Let's see if we can start to predict what the derivative function might look like for nice, smooth polynomial functions. Work through the ministry content linked on our Brightspace page with the help of your Desmos derivative machine. For each new example, enter the given equation for f of x in your Desmos derivative machine, and then use what you find to fill out the given table. You will do 2 parabolas, 2 cubic functions, and 1 quartic function. Please ignore any instructions about tools or curve expert, and then we'll meet back here in 15 minutes, or if you want to pause the video and work through this on your own, or whatever your current circumstance is, just please make sure you've had a chance to work through and try this stuff out. Once you are done with that activity, please proceed with the video. And I'm going to move on, assuming that you've looked at those graphs, you've worked through, and you've started to notice a pattern between the function that we're given and the graph of its derivative. And so what we're going to see is we're going to take a look at our different f of x's, so our given parent functions, and talk about what shape did the derivative curve have. So in our first example, we have a line. And we've noticed some of these trends before. I pointed out a few of them. So maybe you've started to pick up on this already, or you just figured it out now as you worked with the Desmos derivative machine. But one of my original function is a line. My f of x function, or f prime x, sorry, is going to be a horizontal line with a slope of 0. 0. So that's going to look something like this. Y equals a. And the other type of parent function I might have is a parabola or a quadratic. And so my tangent lines had a negative value, and then 0, and then positive. And so the shape of my f prime of x was just linear. So some line with a non-zero slope. If I have a cubic function, which looked something like this, then I might have noticed that my slope was, or my instantaneous rates of change were positive, and then 0, and then negative, and then 0, and then positive. So that would have been a quadratic. So parabola. And then when we looked at a quartic function, we might have seen that our instantaneous rates of changes were negative, and then 0, and then positive, and then 0, and then negative, and then 0, and then positive everywhere else. And so the shape that's going to give us that kind of pattern is a cubic function. And we might have looked at a quintic parent function. Let's see if I can get this one. I think that's right. And so we might have noticed once again that our instantaneous rates of changes were positive, and then 0, and then negative, and then 0, and then positive, and then 0, and then negative, and then 0, and then positive. And what shape is going to follow that pattern? That's going to be a quartic function. And hopefully you're starting to notice a trend here. So I had a line here, and this was a line. I had a parabola, and this was a parabola, and cubic, and this was cubic, and quartic, and this was quartic, and so on. So what can we say kind of in quick general terms? Well, we can say that polynomials are predictable. Predictable. And that's a good thing. That's going to make our life a little easier as we move forward. Let's also answer this question here. Are polynomial functions differentiable everywhere? And the answer is yes. We've kind of discussed this previously, but anytime I'm dealing with a polynomial, just like we saw with these examples here, There's no restrictions on the x value. X is an element of the real, is our domain, so there are no restrictions. Think about the other reasons that a curve might be not differentiable. We might have like a cusp or a corner. We're not going to have those in polynomial functions. We might have a hole. We're not going to have those in polynomial functions. We might have a jump discontinuity. Nope, we only have that for things like our piecewise functions. And the other thing we might have is an asymptote. Once again, those are only going to show up in something like a rational function. And our final case was if our tangent line was completely vertical, and that's not going to happen. As I extend, part of, let's say, my quadratic function further and further to the left, that value is going to get really, really steep. I'm going to have very high values for my rate of change, but it's never actually going to be vertical. It's always going to be slightly non-vertical, never straight up and down. What if we want to be more specific, though? Here we just talked in general terms. How if my parent function is a quadratic, my f of x is parabola, then my f prime of x is linear, or if I have cubic, I'm going to get a quadratic. How can I find the actual function? So if I start with my cubic f of x, how can I actually find my quadratic equation for my derivative? Well, go back to the first principles definition of the derivative. Going back to basics, going back to our foundational knowledge is usually a good bet, and foundational knowledge and having structure and going back to basics is always going to be your friend when you get stuck. So let's take a look. Let's use first principles to find the derivative of f of x equals 1 over 3 x cubed. And so what are we trying to find here? We're trying to find our dx of f of x, or we're trying to find our f prime x. And just a quick note, f prime x and f inverse x are not the same thing, so be careful with your notation. Please don't confuse those two. Let's work through this. As always, we're going to start with our definition, especially because it says using first principles. So f prime x is going to be equal to our limit as h approaches 0 of f of x plus h minus f of x over h. And let's start substituting things in. Equals limit as h approaches 0. And for our given question here, our f of x is equal to 1 over 3 x cubed. So I'm going to have 1 over 3 x plus h cubed minus 1 over 3 x cubed divided by h. And this is a little ugly because of the fractions, but we'll make do. All right, let's go to our next line. The tricky part here is going to be dealing with my cubed term here. So we can kind of do this off to the side. We can do x plus h times x plus h times x plus h, and that's going to be x plus h times x squared plus 2hx plus h squared. And we can expand that again. X cubed plus 2hx squared plus h squared x plus hx squared plus 2h squared x plus h cubed. And do we have any like terms here we can collect? We have a couple. So hx squared and hx squared and h squared x and h squared x. Be careful. Make sure you don't confuse those two. They're not the same thing. So x cubed plus 3hx squared plus 3h squared x plus h cubed. And if you remember working with your binomial expansion, I know some of you may have done your grade 11 or grade 10 math during online learning in the last year, and so maybe your course skipped the binomial expansion. But if we draw Pascal's triangle, 1, 3, 3, 1, so we are using binomial expansion. And we notice that our coefficients here match these coefficients here. So if you want to use that tool for expanding, that's fine. I'm not going to discuss that. It's not technically part of our course, but it is something that you may have encountered somewhere, and you can use that as a tool for expanding binomials for to varying degrees. Anyway, whatever way you decide to do it, this is the value that we need. Let's put that into our equation over here. So equals limit as h approaches 0 of 1 over 3 times x cubed plus 3hx squared plus 3h squared x plus h cubed. And the nice thing about these questions is we at least know from experience they will simplify nicely. It won't be like this the whole time. Minus 1 over 3x cubed times 1 over h. It's a lot easier to write than that big dividing line with the h on the bottom. All right, I'm going to rewrite this a little bit again. Limit as h approaches 0 of 1/3 times x cubed plus 3hx squared plus 3h squared x plus h cubed minus x cubed, so I've kind of factored out the third, times 1 over h. And now that I'm multiplying two terms inside here, I can actually split this up. So I can rewrite this as limit as h approaches 0 of 1 over 3 times limit as h approaches 0 of our other portion. So we're going to have, once again, x cubed plus 3hx squared plus 3h squared x plus h cubed minus x cubed 1 over h. And actually, there was a like term I kind of missed here. I'm going to just edit this rather than rewriting it because I don't want to lose stuff here. So x cubed minus x cubed, those are going to cancel. So I actually don't need to rewrite those down here because they are gone. So limit as h approaches 0 of 3hx squared plus 3h squared x plus h cubed times 1 over h. And what do we notice now? Well, every term here has an h in it, so maybe I should factor that out. So limit as h approaches 0 of 1 over 3. There's no h value in here anymore, so the value is just going to be 1 over 3. There is no h to approach 0. So 1 over 3 times limit as h approaches 0 of h times 3x squared plus 3hx plus h squared times 1 over h. Now I have an h in my numerator and in my denominator, so we can cancel those out. And I think we're ready to find the limit, or take the limit, because we can't simplify any further. And I've gotten rid of my h in my denominator, which is the trouble area we always have to watch out for. So we're going to have 1 over 3, 3x squared, plus 3 times h times x, so 3 times 0 times x, so just 0, plus h squared is 0 squared, so 0, so I don't need that. So that's going to be it. So we're going to have f prime x equals 1 over 3rd times 3 is just 1, so that kind of cancels out. So I'm just left with x squared. And what do we know about x squared? Well, that's a parabola. So therefore, d dx of 1 over 3 x cubed is equal to x squared. And what do you know? That's a parabola. So we said in general terms up here that our cubic function is going to have a parabola as the function of its derivative. And we just showed that down here for a specific example, that for our cubic function, our derivative is a parabola. Interesting. I'm going to stop this video here, and in the next section, we'll move on from our nice smooth functions, our nice polynomials, to talk about derivatives of not so nice, not so smooth functions.